Today I'm going to be talking about spatially and temporally resolved imaging of multimode fibers. This is a generalization of the popular technique of spatially and spectrally resolved imaging, S-squared imaging, which is used to characterize the modes of a multimode fiber. So I'm going to start off with a brief overview of S-squared, how it works, but also some of its pitfalls and how they're resolved by spatially and temporally resolved imaging. Alright, so this is your typical sort of S-squared setup. We've got a broadband source like ASE. You couple that into your multimode fiber for whatever particular launch condition you want to characterize. Then at the other end of the fiber, you've got some imaging optics, polarizer, and a single mode fiber attached to an optical spectrum analyzer. And then what you do is you raster that single mode fiber across an image of the output of the multimode fiber, and you take spectra at each point in space. So what you end up with is a spatial X versus spatial Y versus spectrum dataset. And from the beating between the modes, you can infer something about the differential mode delay. So here's how it works here. We've got the spectrum off the optical spectrum analyzer. Fourier transform that into the time domain to get differential group delays. And then if you take the amplitude of each delay for each point in space, then you get an image of what that delay looks like, and because different modes have different delays, you get images of what those modes look like. And that works pretty well. The advantage of S-squared imaging is that you don't need anything particularly complicated to get it to work. You just need a broadband source, optical spectrum analyzer, translation stage. There's also another version which has a tunable laser and a CCD camera. So in both cases, the kind of things most labs have sitting around somewhere. But the problem with S-squared imaging is that because we're working with, say, an ASE source and an optical spectrum analyzer, there's no spectral phase information. So when you do that Fourier transform from the wavelength domain into the time domain, it's not completely valid. It only really works when you've got one strong mode, which you can assume to be your reference, and you just assume that all the beating occurs between the reference and the mode of interest. Beating between the smaller modes or the weaker modes can simply be neglected. And that's what we can see here. So let's say the true temporal response is as seen in blue there, 4 different modes, 4 different delays. Fourier transform that into the wavelength domain, then throw away the phase information like an optical spectrum analyzer would, and transform it back. And you can see that when one mode dominates, that reconstructed red temporal response is valid, except for the fact that it can't tell the difference between early and late arrival times. You just get an absolute value of differential group delay. But as all the modes become of pretty similar strength, you can see the reconstructed starts to deviate quite a lot from the actual temporal response. The way around that is to get the spectral phase information, and then when you go and do the Fourier transform into the time domain, you get the actual impulse response. There's a one-to-one relationship between the spectral response you've measured and its corresponding temporal response. Everything is unambiguously specified. You've got all the information. And to get that phase information, you can use a swept wavelength interferometer. What that'll give you is the Jones matrix of the device under test as a function of wavelength. So you get all spectral phase information, but you also get all polarization in and polarization out state information as well. Okay, so the example demonstration I'm going to give here is characterizing a 19-cell photonic bandgap fiber. It's 5 meters long. And I'm going to be using this arbitrary mode generator at the input to produce an arbitrary spatial and polarization state to launch into the fiber. We're no longer constrained to just the case where we have to have one strong mode and a bunch of weaker modes. Now I'm just going to launch a whole group of modes, all of sort of fairly equal strengths across from the lowest order mode to the highest order modes. This is what the arbitrary mode generator looks like. It's a spatial light modulator based device. It's got an array of input single mode fibers that comes into the polarization diversity optics, which splits the horizontal and vertical polarizations onto the left and right sides of the SLM respectively, allows the SLM to address each polarization independently. I typically show the SLM as if it's a transmissive device because that's clearer on paper, but in reality the SLM is actually reflective like most are, and the inbound and outbound optics are kind of stacked up on top of each other, like so. Then the outbound polarization optics recombines the beams and then couples it into the multi-mode fiber under test. And this is where we're going to be exciting a superposition of many modes. Gaussian comes in, hits the phase mask, gets converted to the desired mode, coupled into the fiber. At the output of the fiber, we've got another SLM system, which in this case is just being used as a kind of overly complicated translation stage. So this is typically an S2, where you'd have your mechanically rastering translation stage holding the single mode fiber. In this case, we're using the SLM just like a little tiltable mirror, which scans the single mode spot across the core of the multi-mode fiber. And then for each point in space, we take a sweep with our swept wavelength interferometer. So the swept laser goes into the arbitrary mode generator at the input, excites a whole bunch of modes. Then at the other end, the detector is attached to our SLM translation stage. And that gives us a data set which is spatial X versus spatial Y versus time versus polarization in versus polarization out. And here's one example across the C-band from 1525 nanometers to 1566 nanometers. So you can see if you scan through the delays, on the right we can see what each polarization in and each polarization looks like at that particular time slice. So you've got some sort of discrete peaks for the early delays corresponding to modes which were excited at one end, traveled pretty much through the whole fiber as is and exited in the same mode they went in. Then through the middle you've got this sort of more distributed scattering, which is occurring along the length of the fiber, and then you got a bit of a gap. Then you can also see there's a sort of island by itself there for some of the surface modes. But because the modal chromatic dispersion of this fiber is actually very high, what we're actually seeing here is a mixture of modal and chromatic dispersion, all sort of superimposed on top of one another. If you want to sort of tease them apart, what you can do is just pick off a slice, or just pick off a small section of your spectrum, in this case a 256 gigahertz window around 1550, and then Fourier transform that to get the spectral response, to get the temporal response in the vicinity of that wavelength. And here we can see that the discrete peaks for the different modes become clearer, but you've still got the same general trend: lower order modes, discrete peaks, and the sort of more distributed scattering occurring across the length for the higher order modes, and then the surface modes at the end as well. Should also be pointed out that we don't just get the amplitude images for each delay and each polarization, you also get the wavefront as well, and that's what we're looking at here. The phase images for each polarization in, each polarization out, for every delay. Another interesting way to display the information is through a spectrogram. In this case, it's the temporal response at each wavelength. So like a sliding window Fourier transform, you pick off each wavelength, get its temporal response, and then make this sort of waterfall plot here. For the lower order modes, nothing too exciting, not very dispersive, it's all pretty straight lines. You can actually see splitting of the 4 different types of LP11 modes into quite discrete delays. Then as you head on to the higher order modes, things start to get very complicated very quickly. I can see some of these modes are extremely dispersive, presumably as they're coming in and out of cutoff. And then you've got the sort of bit of a gap there in the surface modes off at about 1.6 nanoseconds. The other thing you can do with the spatially and temporally resolved imaging is you can actually evaluate multiple different launch conditions in the same experimental run, because everything's resolved properly in time. What you do is you assign each different launch condition you want to evaluate a different delay, and then they'll just show up as separate windows of time in your impulse response, and they can be analyzed separately. Here's the example I'm showing here. You've got the swept laser coming from the swept wavelength interferometer. You split it in 2, delay one arm. One of the arms goes on to be a center launch. The other arm goes off to be an offset launch. And then when you look at it in the time domain, they show up as 2 different windows, evaluating both different launch conditions in the same go. Got the offset launch on the right and the center launch on the left. And you can do this for as many different launch conditions as you have laser power to split up, basically. You're not limited to just 2 launch conditions, obviously. If you've got enough laser power, you can split it up as many times as you like. Just as long as you can capture enough time on your SWI to fit all the impulse responses in, and also obviously as long as you space your different launch conditions out enough in time such that they don't overlap. Hence, you could do multiple different offset launches. You could launch different modes using different phase masks with different delays, or you could even do something like launch in using a photonic lantern, put different delays on each single mode port of the photonic lantern, and evaluate the entire mode basis of that fiber in one go. Alright, thank you very much. Hopefully I've shown that spatially and temporally resolved imaging overcomes some of the limitations of the more traditional S-squared imaging technique. Namely, you can launch any mode superposition you wish into the fiber and then characterize it unambiguously. It also gives you the added benefit of getting all your polarizations in and all polarizations out at the same time, as well as giving you the ability to evaluate multiple different launch conditions in the same experimental run.